Okay, so this is chapter 18 of Wiley. And basically, the first thing I'm going to do is introduce everybody to Lewis acids and bases. And the main thing to understand about the nature of them is that with a Lewis acid, it's an electron pair receptor. So an obvious one is aluminum chloride like this. You have aluminum like this as 3 electrons around it like that. That's its electron configuration. You put the chlorines here, here, and here, along with the dots around it. That's aluminum chloride. And then there's this empty space here, which can take an electron pair, okay? So basically, this is electron pair receptor. Boron is another example of another one like that, because they both have an empty orbital here in there for an electron pair. So that's an electron pair receptor, okay? Even just a proton, even for a hydrogen atom, can accept an electron pair for something, just like from a chloride or something like that. So that's the HCl there. So basically, you got the chloride coming in there. This is plus, and then you got the HCl. So basically, the Lewis acid is the first concept. The Lewis base would be something that looks like this. And then you got the electron pair there. So where can this electron pair attack? And I'm going to ask Robert this. Where can this electron pair go, Robert?
Sorry, what are you asking?
This electron pair, where can it go to attack? It's electron pair donor. Donor to what?
Goes to other places that allows for electrons to be accepted.
Right, it'll go right to here, see? And then you got the boron here with the hydrogen around it, like that, and then the nitrogen, and then the hydrogen around that one. So basically, that's a compound of the combination of them. Okay, So that shows this is an electron pair donor, this is electron pair receptor. And just so you know, Jorge, I'm going to tell them that I will start talking about Lewis acids and bases in the first chapter of Organic Chemistry 1. So they'll have this thoroughly. That's the way I teach it, is by talking about Lewis acids and bases. I believe that Wiley, the textbook, talks about the other Brunson Lowry, which is not really helpful. But in any case, so that's.
Well, we can sort of come back a little bit again. Like, what's the main topic you're talking about again?
It's aromatic substitution reactions, and
okay.
essentially what's going on. You got a benzene ring that looks like this. Okay, that has electrons on the top and the bottom. So it's like it's shaped kind of like this here. And then you've got an electron cloud on the top and one below it. And there's a hydrogen for each one sticking out like that. Okay, and then you've got a bromine coming in here in some way, and it goes in and attacks here, leaving this thing now, and then now you have a substance that looks like this with a bromine on it, and the hydrogen is gone.
And this aromatic substitution reactions is only caused or associated with this benzene ring?
Yeah, that's essentially what the topic is about: electrophilic aromatic substitution. And so basically, electrophilic is the first one. Electrophilic, and I'll talk about that on the next slide. But basically, that's the background for this.
Okay.
Okay, now electrophile is electron loving. Okay, so it's a Lewis acid. So it's like this aluminum chloride is an electrophile because it has these 3 chlorines around it and this empty space. Okay, and that's a Lewis acid. So any of those other there. The nucleophile is nucleus loving. In other words, the nucleus is a positive center, and it could be any negative ion. It's attracted to any negative ion, which is a Lewis base that it gets attracted to it. So basically you get the nucleus and then the Lewis base. So essentially it attracts any negative ion. So essentially that's what is involved with an electrophile, which is, this is electron loving. It comes from the Greek, and this is the nucleus loving, or the positive loving. And basically it essentially looks for electron pair. So that's a Lewis base, which is electron pair donor, which gets added to it. And then the Lewis acid is electron pair acceptor. So that's the thing. Now, the topic today is essentially with electrophilic aromatic substitution. In the previous chapter, and obviously you didn't see the previous chapter, Robert, but basically aromatic bonds are less reactive than this alkene, for example. If you react this alkene, this double bond with it, this bromine will come in and attack, and it'll be like this, Rob, and I kind of explain it like this. You got the double bond here. The bromine comes in like this. Then this bond, and this bond break, and then you got one to the bromine there and to there. So this bond is breaking, this bond is forming, and now you have this new structure here from just this double bond, okay? And then with the benzene ring, you've got this electrons all around the top and around the bottom, and this does not happen. This does not happen because it's not reactive enough, because this is stable. This is much more stable because of electron pairs above the cloud, above and below the six-membered ring. So basically, it's not very reactive that cyclohexane would be. Okay, so that's the concept of electrophilic substitution. But aromatic is when you have got a benzene ring. When you add iron to the system, and usually this is in the case of FeBr3, like this, Fe plus 3, and then Br3, which is a thing, you have the iron here, which has the bromine coming in like this, the bromine here and the bromine there, and then the open space over here, this bromine comes in next to it like this here. So you got this electron pair, electron pair, electron there, forms this complex. Okay, and because this drags electrons towards the iron on these other things, this gets a slightly positive, a partial positive, and then the partial negative on that end. And so basically this partially positive thing will attract to this electron pair there and kind of get in there to form the bromine on the thing at the end product. So essentially this is called electrophilic aromatic substitution. Okay, now there's a whole bunch of different electrophiles and nucleophiles where the ring is acting like the nucleophile. It wants the positive thing, attracts to it. And remember, these are all electrons going around it. These are available electrons for sharing. So essentially they're a cloud above and below, and it doesn't really matter whether they attack from above or below, you still get that. But you can bring in bromine, chlorine, nitrate, nitrous, and all these other substituents in different reactions. And there are a bunch of different reactions associated with this. Now, in the bromination of alkene, and this is from Organic Chemistry 1, the bromine acts as an electrophile because you've got a slightly positive region here and a slightly negative region there. And basically there you have to have a Lewis acid catalyst is needed to make the bromine electrophilic enough to go to an aromatic ring. So in the case of just the bromination alkane, an alkene, all you have to do is mix the two together and it will automatically go to form this ring like in the first slide. So you get the bromine here and the bromine there, just because you got this positive that gets attracted to the electron pair there, and then it kind of mixes in there with this, and then you get the combination of both, whereas you need a catalyst to make it, and basically you have the iron and the bromine there, and this is a Lewis acid catalyst that looks like that. Sorry, looks like this, with the bromine here, bromine there, and the bromine there, and this is a positive thing, and then the bromine will come in and attack. The bromine will come in and attach to this here, and then you've got the slightly positive part here and the slightly negative part there to kind of get the combination of these factors, and you have that catalyst that's involved in the situation. So essentially what you get now is an active complex where this electron pair goes there, and to kind of get these two together. So you got the FeBr4 minus, okay, and you have the Br plus associated with that, and that is a more potent electrophile, because notice this electron pair is gone. It wants electrons from that benzene ring. So if you got a benzene ring here like this with available electrons, this will come in and attack it there and essentially go into a spot and form a bond there, and then essentially you'll have the hydrogen come off, and then that bond this will pop off there to give that. But basically that's the mechanism of what happens. But essentially here you've got this complex that occurs with this. Now, the mechanism for this, and again, this is acting like the nucleophile. This is a nucleophile. This is the electrophile. So essentially you got this complex that forms with different positive things in there. And then this new FeBr4 minus will come in and abstract this hydrogen, because now this hydrogen is a better leaving group. So essentially this will become H plus coming off of that, and then this electron pair will go back to cancel that out, and then the bromine is left in place. So do you see the substitution there, Robert? Essentially the bromine from here came in there, attacked there, and the hydrogen left. You replaced the bromine with the hydrogen. Sorry, you replaced the hydrogen with the bromine.
Does this happen automatically, or you have to allow it for it to happen?
In the reaction conditions, in the reaction conditions of the vessel that you're cooking it in, or something. These all it's like cooking. It's like it all happens in a pot. As Jorge could tell you, it's like when you mix food together to make something, you get a combination of reactions that occur with this. So basically, this is cooking in a laboratory. So basically, there's all reaction conditions of this, and heat is part of this because it kind of promotes that. And essentially, the step one is the aromatic ring attacks the electrophile. This is the nucleophile here, and the electrophile there. And I like to kind of view it as this positive thing will attack there. Sorry, this positive thing will attack there to attach this bromine to it, and then you get the reaction taking place, and then this there, and then the deprotonation is the second step. So this is the slow step, and this is the fast step. So essentially what indicates the kinetics of the situation, or how fast the reaction goes, this is the reaction conditions depending on the different factors, what the temperature is and other factors to that. So that's one example. Now, addition reaction